Okay, today I'm going to go over quad trees, and then I'm going to do the study guide, and that'll be basically it for the class. Hopefully I have enough time to cruise through the study guide. There's a pretty long section in it, so this may be a little longer than normal. All right, but first let's go over quad trees. It is good to at least, at the end of this course, go over at least one extra data structure, just so you can see how new data structures really relate to the core data structures we've gone through. The thing to keep in mind is the ones we've gone through, and when I say core, I mean they're really the foundational data structures that most other data structures come from. Okay, I've said the word data structure so many times. Anyways, so today we're going to look at quad trees. Well, you can already tell by the name that it's a tree, kind of like a binary tree or a B tree, but it has the word quad. What do you think that means?
There's 4 nodes.
Whoa, okay. There are 4 nodes. And we'll go through what it's useful for. It's actually really good for doing 2D collision detection inside of games, which is why I chose this, because it is a game structure. I said 2D, so that's with quad. So you want to take a guess what type of tree to use for 3D? Nice, an oct tree. All right, good. So this can easily be extended to 3D, and then if you really wanted to go to 4D, you could, although, yeah. All right, anyways. All right, definitions, etc., blah, 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 blah. It's nice. All right. A quad tree is a tree data structure in which each internal node has exactly 4 children. Yep. In a quad tree, each node represents a bounding box. Okay, so we have a bounding box. The idea is that you have this 2D realm, so to speak, and this may be a little hard to see, but you first have the box, and if you want to cut up the big box, let's see, do we get a little picture? No. Okay. So if you want to cut up the box into 4, sections, well, you cut it halfway and both vertically and horizontal, and then you have 4 different boxes. Well, if it's a quad tree, then you can keep chopping it up. So for example, you chop it up here and here, so you have 4 quadrants, 1, 2, 3, 4, and then inside this one you can chop in the middle here and here. Let's say we're trying to get that dot. And so then you would have this box, and then you chop it up again to 4 quadrants, 1 quadrant here, here, and here, and then you look at this box, chop it up again, until you finally have a box that either contains either the 1 node, which is what we're going to do in class, although I'll tell you, in real life, usually they put up to about 5 nodes in it, because searching a list of 5 is pretty fast. There's not really a need to chop it up more. But for this one, you keep going until there's only 1 node, and then you say that node is in that box. All right. Perfect. So how do we insert this? Oh, here we go. So you might have the picture of the entire field, and then here are the different ones. You get upper left, upper right, bottom right, and lower left, and so those are the 4 children. And then this guy over here may then represent the 4 boxes inside of it, so upper left, upper right, and lower left. So they're doing it clockwise. How are we doing? Great, good. So to query a tree, aka where is this thing? Let's see, starting at the root, examine each child node and check if it intersects the area being queried for. And if so, if it does, recurse into that child node. Whenever you encounter a leaf node, examine each entry, and if it intersects with the area, return true, otherwise return false. Again, this is usually used for collision detection, because you might have some object that's around here, and so you'd want to be able to recurse quickly into these different coordinates to see if there's some type of collision. All right. To query a quad tree, starting at the root, examine each node. All right, we just talked about that. Ooh, this is a nice old picture. Look at all of that. I don't know if that's helpful. I don't think it is. We're moving on. Oh, look at these guys. I don't know why. Oh, I totally stole these slides from some guy, as you saw from the beginning.
Yeah.
Maybe they wanted to put their picture in there. And have more pictures. All right. Okay, even more pictures. There we go. example quad trees. All right, first off, there are different types of quad tree. I don't know why the slides are doing this. This is the type of quad tree we are not doing. So you could make a two-dimensional binary search tree. First point is the root. The shape of the tree depends on the order of insertion. This is actually really, really confusing to follow. It looks like what they did is they first cut it right here. So you have a top half and a bottom half. And they put Chicago right here on this line. And then what they have? Toronto. So Toronto, they decided to cut up here. Okay. As one of the children, sure. And then you can have another 4 boxes. The idea of this point quad tree, why it's somewhat helpful, is that you, by changing it by points, you're actually jumping to individual nodes, which can be very useful. The issue is that for collision detection, it's kind of confusing. So, don't do this. We are going to be doing a PR quad tree, which when you look at the math looks like this, which I know makes perfect sense to all of you. Wait, actually, y'all are in discrete math, aren't y'all? Okay. Yeah, well, oops. Now, if you go back to the regular quad tree where things are cut up, so you have your initial point, you got the northeast, northwest, southwest, southeast. Notice the northeast section should have nothing. Why does it have 2 and 3? What's 2 and 3? Oh, northeast up here.
No, that's west. East is to the right.
Whatever. There we go, northwest. All right, northeast, that's Toronto, Buffalo. That makes way more sense. Whew. And look at which coordinate it is in. Perfect. And then the southeast, which is on this side, Atlanta and Miami, northwest section, southeast section, and then notice here up southwest. What in the northwest section there, northwest? That does not make sense. Northeast,
section.
Thank you, as mobile. Wow. Okay, never take directions from me.
With relation to the compass. I'm
Yeah,
sure
no, just period.
Oh, just period.
Just period now. Over the hill, take a left, or maybe it was a right, whatever. Okay, so in the southwest, the northeast section knows that since there's more than one point, they chop it up again, and then you have your 4 different towns or cities that are in that section. Great. Oh, we have theorems. And then we proceed to a lemma. Okay, the depth of a quad tree for a point set of P points in the plane is at most, C, but we haven't defined what S and C are yet. Okay, good. Where C is the smallest distance between any 2 points in P, and S is the side length of the initial square that contains P. Yes, that is correct. Sure.
I don't think they defined S.
Yes, they did. Is the side length of the initial square that contains
P
P.
and S?
So up here, the side length is S divided by 4, because if you would, there would be 4 of these blocks across the line.
Okay.
Or 8, sorry, divided by 8. All right. Good. And the depth is 3. Perfect. Quad tree of depth at E storing at most endpoints has nodes and can be constructed in effectively O of n time. An operation. Okay, are we going to actually talk about it? No, we're not. Okay, well, let's go back to this picture. So you fill this all out. What's the big O of finding something? Which is the whole point of this thing. You said in-law again? Where, sure, why do you think in-law again?
So most of our searches have been so far.
To search something? Well, we start at the beginning, right? We figure out which one we go to. When we go to the next node, how much of the tree did we just chop off?
3/4 of it.
3/4 of it. So we're going to the 1/4 that matters.
that log base 4.
There we go, log base 4. We'll just say on average. If it was equally distributed, log base 4, which is what we go with. Is that faster or slower than a binary tree?
Faster.
It's faster, and yes, it is substantially faster. Okay, I think we need to get to coding. Thanks. All right, well, actually, before we get too far, oops, lab 24. All right, in case you didn't see it coming, we're going to implement a quad tree. Hey, look, we're going to be the class will begin to fill this out. What are we doing? We're adding, we're removing, we're asking if something contains, and then we're just going to count if and range. Today, I'm not going to go over how you do full collision detection with the quad tree. You can go look that up if you really want to. It does take a little more coding, but I want to at least make things simple at the end of the course. Unless you want me to make it complicated, then I can. All right. Okay.
Is this the data structure people use when they make like boxes or whatever? Do you know what those are? I always hear people talk about like boxes where they like how much of cubes.
All right, hold on. All right. We have boxes everywhere. Instead of like drawing people, we draw boxes, and then we say this is a person. So when you say box, I don't know what you mean.
Oh no,
bounding box or
no, with the V voxels.
with the, I'm sorry, what?
With the V.
The V?
Yeah.
Like 3D pixels.
Oh! When you're actually drawing a box? Oh no, that's done with matrix transformations.
Okay. Never mind.
Well, all right, class to begin filling out. So, what is this quad tree going to be made of?
Not a vector. We've done that before.
Not a vector?
Not a vector. We've done that with these.
Okay. All right, we have to have a node.
Oh, we could use a B tree from the STL, right?
Does the STL have a B tree?
I don't know.
I don't think it does.
That would be awful.
Someone go look that up real quick. That'd be some serious cheating. Oh, no, you can't. Because the B tree is going to order it left and right.
Oh.
This ordering is very different. Yeah, you're not going to be able to use a B tree. Good try.
That's what I was told to do by all the people who passed this class. Use the STL.
We can use one of our old features.
No, the B tree is not going to work.
And then don't sort it. Never mind.
All right. Someone said we need to have a node. That sounds great. What should the node contain?
Looks like a float.
It would have to contain at least 4 pointers and a float value.
All right, so we're going to have 2 floats. Yeah, if you look at the, we're adding 2 floats, so we're adding a point, and I just used floats. Oh, when you make the quad tree, it has a width and a height. That's cute. All right. So it looks like we're going to need to have a class. What do you want to call it?
Node.
Man, we're uninventive. I'll at least call it the Q node. There we go. All right, what should it have? Go. I'm done typing. Oh, that was some interesting.
Yeah, I like those.
I also like how there were eyes and float. Well, float value. Oops. Well, the float is an XY, right? So there's 2 floats. Probably should call it X and Y. Maybe. I don't know. Perfect. All right. And what else should it have? What's that?
Oh.
I was just following it. All right, so you have some pointers to other Q nodes. Cool. Let's create a default constructor. That way we don't have any problems. All right, that actually looks pretty good. So then what's our quad tree? Good. We have root. All right, we do have to store something else.
Number of divisions.
Well, it's width and height.
Ugh.
You're the foe. Amazing. All right. Anything else? I don't remember. We'll find out. So set it equal to null. Wow, that's weird. I'll go and give this an underscore so we can make it easy. All right. So how are we going to add? Oh yeah. First, let's make sure we fail some test cases. Oh, good. Here we are. So quad tree, 1,000 by 1,000. We ask if it contains 100. It shouldn't. We add 100 and 100, and then she contained it afterwards. So let's see. Do we fail? Let's go with, I guess, a new window. We passed. Well, that's not good. How did we pass? Add is false. Contains. Oh, let's just return false at all times. Of count and range, return -1, and then we'll return false on the remove. All right, we started failing some test cases now. Thank you. That was amusing. Okay. How do we add? Let's take the easy situation. We're adding 1 point.
So we just go to the X and Y coordinate. What do we add?
Well, right now, what's our root node? It's pointing to.
I guess the whole tree.
The null potter. Make the node.
Yeah, let me do that.
Root equals new, whatever. Oh no, you don't necessarily need to make a new node.
Not every time?
Mm-mm.
Okay.
Ooh, we made a caret Z. That's cool. think you were correct with the root, because we're saying that if the root is null, then you want to go ahead and set the root to a new node. So we don't have a node to add at this moment.
Do we have a constructor for QNode though?
Yes, it just sets all the pointers to 0. So we probably want to set the Q node, create the new Q node, and then set the XY.
Yeah.
Yeah.
Okay.
I don't think we pass X and Y.
Yes, it's
Cool, we could. All right, and then we return. Okay, amazing. All right, let's see if that passes any more test cases. Oh, yeah. Hmm. 17, fail. Oh, you know what? Probably because we need to see if contains works. All right, let's make contains pass. All right, let's go see if that passes. Nope, now we fail on line 16. Why? Because remember, we first ask if they it doesn't have it, then we add it, and then we ask if it's there afterwards. Good try, I liked it. You're thinking the right way. Believe it or not, that is the right way to think about this. Good catch. Good catch. Oh man, you're getting good. All right, I love this. Hey, we passed the first one. Good job. And then we failed the second one. All right, what's the next one? Now we add multiple of them. Oh, we have a print function. And we ask if certain ones are contained in them. Excellent. All right. So, now we're here where we want to add something. Alright. Where does it go?
Good question.
Ooh, we're gonna rover it. Well, let's pretend we don't rover. The reason I say that is just to make this easy at first. Let's say we're only dealing with the root node. Start with the simple case and then work up. So we're working with the root node. We've already confirmed that's not part of the root. What do we need to figure out next?
It's northeast, southwest.
You got it.
Check both lines, anyways.
x is greater than root dot x. Wait a minute. We can do it this way. This is the other quad tree, and this is actually fine. Sorry. Oh yeah, do we call it any?
No, it's just.
Oh, okay. Okay. So this is fine. I just want to point out that we're not doing this quad tree. We're doing this quad tree, kind of, sort of, which is actually just fine.
Nice double semicolon.
Excellent. Yep, you gotta do the if again.
You're supposed to be root.
So hold on a second. Do you want there to be a third case to this if statement,
Yeah.
or do you want to just be two? I'm
I
pretty
guess you can
right.
Return false though.
Right on both. So the point I'm trying to make here is we really want to say if this, go on that side. Otherwise, we're just putting you on the other side
Yeah.
because we don't want a third case to that if statement, which would make it more than a 4D.
I was thinking you just returned false, but yeah, it still makes sense.
Yeah, we got to put all the points in there. They've got to be stored.
Okay.
We are really ending that statement. Yeah, so, and then we return true at the end, right? Because we've put it somewhere. It's got to have gone somewhere. False equals true. Wait a minute. True. Now that one I've done all the time. T-U-R-E. Oh my goodness. All right, let's save that and see what happens. Hey, line 30. We're still at the same spot. Because we always return true. Oh man. All right. So. Oh my goodness.
Got us this far.
All right. Well, it was fun while it lasted. So we actually need to put in some extra coding.
Heck, actually, that needs to work though.
So what do we need if we're doing contains? You have x and y. What do we need to test first?
Can we just copy the if statements from the other one? See where it is.
Sure, but before that,
Check if the x and y are actually valid.
check if they're valid. Yeah.
Oh yeah, because we have a width and height.
Yes, we do.
Do we have a math thing?
Well, if x is less than 0 or greater than width,
Oh yeah.
yeah. Less than 0 or greater than width.
Oh yeah, if it could be negative. Right,
Yeah, okay, so there are different ways to do this, and I'm in this class, I'm always assuming, is it in here? Well, anyways, it has a width and a height, and it's always going from 0, 0 to that width and height, is what I'm assuming. So if it's negative, then we're going to say it's not valid.
So 0, 0, like the
Right, 0, 0, we're saying is in the upper left because in computer science land, that's what we do.
Yeah, so
If it's less than 0,
okay, yeah,
then we're going to return false. Okay, or x is. All right, and what else? Yeah.
I don't think I called it width and height.
What will you have called it instead?
I don't know. I would always check.
Number 1 and number 2.
All right. Well, okay. We'll see if that passes the test cases. Shouldn't. All right, same problem. All right, now that we've validated root exists and the x and y are correct, what do we need to test? Yeah. All right. So if we find it there, otherwise we'll just say return false because we didn't find it. Let's see how we did. We passed the first one. Ooh, we failed earlier on the 28. So right here, oh, we get the 100, but not the 700 and 100. So when this guy was added, we didn't look. Okay, that's because it's one of the children. So what do we need to do?
Check the children.
All right, let's check the children. All right, I'll help you out real quick.
oh man, this is a mess.
It's a mess. All right, can anyone see how we can make this not a giant mess?
While.
Oh, we could do a while.
No.
What type of coding did we do with the binary tree?
Recursion?
Recursion. The recursion made things a lot easier. And I'm going to set this one up for you. Let's see. Bool. What are we doing? Contains? All right. So the idea, we could do contains. In this situation, what do we run contains on? The idea is we're going to call the recursive one. So in this situation, root. Hmm. Yep. Perfect. Okay. Now we can either fill out the rest of this or start writing contains, whichever one you want.
Yeah, I'll do this.
All right, since we're thinking about it. Okay, great. Although we want to return from contains. I probably forgot to put that in there.
Ah. Tell you password is, right?
There is, but oh well. Right now, just do it the slightly longer way, and it'll take the 15 seconds. Okay, great. So we're calling contains. Let's go scroll up to that contains function. When we're in here, what should be the first thing we check?
Same stuff as usual.
Okay.
We copy it from the.
Well, we don't need to check the X and Y because we've already validated that. Really, we just need to validate that the node is correct. So let's do that. Extra ifs, just in case. Double equals, or we're going to be really sad. My X's all changed. Yeah. Okay. Otherwise. Okay, cool. All right, let's work with that. That sounds great. Hey, they all passed. Wow, I did not expect that to happen. All right, let's make it fail. Alright, what do we have? So we have 100, 100, and okay, let's go. Let's make it a 50 by 50. And maybe 75 by 75.
I got you.
60, 60. Alright, there we go. Let's see if that I can stop it. Alright, did that fail? Oh, good. Line 46, expression evaluated to false. This one right here. Yep. So, what happened here? We had the 100, and then we made the 2 down there, and then when we tried to make one above it, it did not like that. Let's do a print function. Ooh, this is going to be tricky. This could be real tricky. Ooh. Yeah, how are we going to print this?
Really wish we could use like an overleaf sort of deal.
Not going to happen. All right, anyways. All right, I'll write a quick print function for us. It's gonna be really hard to see, but oh well. And then we'll call print on root. Oh, I don't have the in. Oh well. Oh, that's interesting. That's an infinite loop.
Oh, you did not root. It's supposed to be not node for the check.
Thank you. Oh, here we go. We have 100, 400, 760. Uh-oh. Well, let's see if we can get some printouts of what's going on. Put some lines in there so we can break it up. And let's go print after each of these. There we go. So 100, 400, 700, and then here we go. We add the 50, that looks good. Then we add, oh, it's overwriting it. Hmm.
That means we have to chop it up more.
We're not contained, so oh yeah, look at that. We just put the node in. How silly. We didn't check if these things were null, did we? No. Okay. So technically would have to be if root, let's see, y'all do equal null PTR. Ah. Oh my goodness. Let's see how many lines can we make. Otherwise, what are we doing? We need to chuck it again. Okay. All right. Again, we can make this. Which way do you want to do this? Iteratively or recursively?
Recursively.
All right. So it is important that at least y'all practice creating these recursive functions. So create the recursive add function. Here's the add. We're adding these floats. So we need to somehow pass it up here. Right? good. Save. GT. No, just GT, now colon. Cycles your tabs. See your tabs up here?
Uh-huh.
Yeah. All right. So we're in the recursive one. What's the first thing we need to check? Well, actually, we don't need to really check because we're checking for null pointers down here.
Yeah.
So what are we doing? We're passing a node. Basically, I need to do these checks down here. Let me help you out real fast. Whoops. Well, we don't have our to add. I'll put that right up here, and then we're going to talk about it just a little bit and make sure we didn't make things worse. We did not make things worse. So it's always very important. Oh, sorry. Pass, we're still failing at 49. It's always good once you rearrange things, make sure you didn't just mess it up. Okay. So here, we can put to add, otherwise, what are we doing? Node-any. Yep. All right, before we go down this rabbit hole too much, oh yeah, go ahead and do that. All right. One way to make our lives a little easier. We already created the node, so we might as well just pass the node along. And whoops, I went too far. Or did I? Oh, because we don't want to create the node more than once, is the trick. So then we can just pass along to add, and that way we have the actual node. Let me go ahead and make sure we didn't make things worse. We made things worse. Oh, maybe this is more confusing because then we have to test to add. No, that's fine. Six, and then we just pass along to add. All right, we're back to where we were. All right, do y'all see what I did? Okay, good. Excellent. All right. Now what happens? Oh man, kind of a Yep. Yeah, the quad tree can be a little annoying to all type out. So is the oct tree. I mean, yeah, the oct tree. Yeah. Yeah, yeah. Well, there are tricks to make this shorter, but let's just do it. Whoa, whoa, whoa. No dash SW down here.
Oh, you're right.
Perfect. And, yeah, sorry. I jumping ahead. Got to close this parenthesis. There we are. Okay. Wow. All right. Let's see what happens now. Hey. Now they're in the quad tree. Well, that's good. We now fail at line 50. We're moving right along. Oh my goodness, that was kind of hurts my eyes. But anyways, line 50. So line 50, 75, 75. Let's go to our contains.
Probably the same problem, huh?
Yep, it's the same problem. Well, hold on. Let me make things a little easier for us. So let's just return contains on the root passing an x comma y. Let's go take this thing, shove it up here, and then let me go find the roots and change them to node. Return false, and then we can put this guy right here. Alright, let's go see if I messed anything up. Ooh, I messed a lot of things up. Segmentation fault.
You put a null check contains the first one.
Ah, yeah, we need a null check. Okay.
I wanted to say something, but I knew you were just going to be too fast.
And then, oh wow, we passed it. Okay. Well, that was easy. Wow, I did that. Okay. Should have made y'all do that. Oh well. Wait, are we done?
I think so. I think that was the whole lab.
Oh, you still have to do count and range. Yes. Good. Oh.
And remove, yeah.
And remove. Oh, remove is going to be fun. And you have to do the destructor. All right, so you still have two things to do. Good. That'll give you some good work. But we did half the lab effectively. Yeah. Hopefully. Yeah. I don't know if that works with the autograder. But anyways, any questions? We'll find out. Any questions on quadries?
Oh yeah, the lab. It's not templated.
No.
I got it.
The lab is not templated. Merry Christmas. Normally one other thing with the quad tree, usually when you add something, you have an X, Y, and then a pointer to some data, because that's the object that you have at that location. I didn't put that in there. We're just going to deal with points. I just want to make this lab easy, so there you go. All right, any other questions? By the way, the easiest way to do remove that will pass the autograder is when you find it, set the values to negative. Or actually, no, no, you can't do that because then when you split, because we're doing the first way. So the easiest way to do that is have like a Boolean flag saying it's been removed. You could do that. Or you could try and remove it and try and shift up a node. Ooh, yeah. Good luck with that. All right. Let's stop.